Hello, welcome. In this video, we will discuss the electric flux, right? Now, first of all, let's see what is flux. Flux means the flow of anything through an area normally. When something passes through an area normally, we call that as flux. But when electric lines of force are passing through an area or through a surface normally, we call this as electric flux, right? Now I have three cases here, and then the fourth case is different. Number one is when the field is uniform and the area is normal to the field, or we can say the area vector of this surface is parallel to the electric field, that is electric field is parallel to the area. The flux of this electric field through this area is simply given as it is phi equal to the product of electric field magnitude and the magnitude of area vector, or simply the electric field and the area, right? So from this we have the flux is proportional to the electric field and flux is proportional to the area, right? So more is the electric field, more is the flux, more is the area, more is the flux, right? Now, number two is when the electric field is perpendicular to the area vector. So we have here a surface. The area vector of the surface as per right hand curve rule is perpendicular to it. So it is upward direction, and electric field is going from left to right, that is parallel to the plane of the surface, right? So E is perpendicular to the area. When this is the case, by definition, the electric flux through the surface is equal to 0, because no electric field line is passing through this perpendicularly or normally, right? Okay. But now the more general case is if the electric field is not perpendicular to the area but it makes some angle with the area vector. So in that case we take either the projection of the electric field along the area vector or the projection of the area vector along the electric field. So when electric field is making an angle theta with the area vector, so in that case the flux is simply the dot product of the electric field and the area vector, right? So that is EA cos of theta, where theta is the angle between the electric field intensity and the area vector. So from this we can also have, we can join these two and this becomes the projection of the area along the in the direction of the electric field vector, or we can join these two and we can take the projection of the electric field in the direction of the area vector. So from this relation we can see here the flux is proportional to electric field, the flux is proportional to the area, and flux is proportional to the orientation, that is cos of theta, that is projection of the area in the direction of electric field or projection of the electric field in the direction of the area. So this is now the more general relation to calculate the electric flux. But this is the case when the electric field is uniform and the area is normal. Here the area is area vector is perpendicular to the electric field, or the surface is parallel to the electric field, and this case is when the electric field is making some angle with the area vector. Now the fourth case is if we have a field that is not uniform and the surface is also not plane. So how to calculate the electric flux in that case? I have taken here a charge. So the electric field lines emanated by the charge are in the space in all the directions, right? So the field is radially outwards, means it is a diverging field, it is not a uniform field. I have taken here a surface S, and this surface S is also not plane. So what I do in this case, I consider a small differential element of the area, that is of this surface, such that the electric field through this surface element is, or this area element is uniform, right? Now At this point, we see the area vector of this surface element makes an angle theta with the electric field intensity. Now, electric field intensity at a distance r from the charge is given by q by 4 pi epsilon naught, then it is r square, then it is r cap, where r cap is the unit vector in the direction of the radius vector or along the radius of from the charge q, right? Okay. Now, similarly, if we take the surface element ds, the area vector of this surface element is given by ds vector is equal to ds, and this is n cap. N cap is the normal unit vector to the plane of the surface. Now, by using the basic definition, we can calculate the differential flux through this surface element and then calculate the total flux through the whole surface, that is through this surface S, right? Now, if d phi is the differential flux through this surface element, where we assume the electric field intensity is constant, then E is equal, this d phi is equal to E dot ds vector. So that is q by 4 pi epsilon naught r square, this is ds, then it is r cap dot n cap, right? If theta is the angle between r cap and n cap, or E vector and ds vector, then we can write this as simply it is cos of theta, because the magnitude of the unit vector is 1. So it is q by 4 pi epsilon naught ds divided by r square, it is cos theta. So d phi is equal to q divided by 4 pi epsilon naught. Now I have taken this term as separate. This is ds cos theta divided by r square. So from the definition of solid angle, it is the solid angle subtended by this surface element at this charge q. So this is solid angle here. So I denote this solid angle by the d omega, because it is the differential solid angle subtended by the differential surface element. So it is q divided by epsilon naught, it is d omega divided by r square. Now, if we have to calculate the total solid angle subtended by the whole surface, that is this surface S, so we will integrate over this ds over the whole surface. So it is this d phi over the whole surface, so that is phi. It is q divided by epsilon naught. So integral of this d omega over the surface is omega divided by 4 pi, where 4 pi is the total solid angle subtended by a closed surface at point Q. So this gives us the relation to calculate the electric flux due to a charge at through some surface S. Now, if the surface is closed, that this charge is enclosed in a closed surface, so in that case, this omega will be equal to, it is 4 pi. So then in that case, what we get, phi is equal, it is q divided by epsilon naught, and this omega will be equal to 4 pi, then divided by 4 pi. So this 4 pi cancels. So what we get here, this phi is equal to q divided by epsilon naught. So this is the famous Gauss's theorem, that is the flux through any closed surface enclosing certain charge is equal to charge enclosed divided by epsilon naught. But now the case is, here the flux is three-dimensional, but if the field lines, if the flux is two-dimensional, if the field lines are emanated only in the two dimensions, then we can take an analogy from this relation, and that analogy we can write here as phi is equal to, it is q divided by epsilon naught. Then instead of the solid angle, we take here the plane angle, that is theta, and divided by total plane angle, so that is equal to 2 pi. So it is theta divided by 2 pi in radian.